listen in. For you, take out a sheet of paper, put your name, student ID, pass it around. For you, take out a sheet of paper, put your name, student ID, pass it around. Do the same. So there's 3 pages. Put your name and student ID on it. I will grant you bonus points in the future that will reward you for attending. I do not punish people for missing class. You're all adults, men and women. You can go and leave as you please. But I reward those who do attend. Only looks about like 25, 30% of the class showed up today. So you should get something, should you not? Absolutely. Yeah. So there we go. Make sure your name and student ID are on it before you leave. Next, in physics, we've studied waves, oscillations. You can have a simple pendulum going back and forth. You could have a mass going back and forth. Regular, repeated motions over and over again, and we've seen it in the world. Now we're going to go over a type of oscillation that we call sound. And other types of vibrations. Sound, waves. You can do all sorts of interesting things. The 2 that we are focusing on today are waves in string. Oh, and the other thing, we're leaving early. Yeah, I know. I am a kind and generous dictator. Yeah. So there are waves in string and there are waves in air. And as an example, you remember everybody has played with a jump rope as a child, and you have sat there and had your friend hold one end of the jump rope, and what you do is you sit there and you shake it up and down like a Polaroid. And then what you notice with the particular vibration, the rope moves in a non-chaotic fashion. Like it may bow up, bow down, bow up, bow down. And then there are these patterns in the string where instead of getting a bunch of chaos, you get one where the string maximizes its movement in the middle and the ends are fixed. You have another one where you start shaking it even harder, and what you notice is that there's a point in the string that doesn't move, and then these 2 move up and down. Then there is a situation where there are 3 that move up and down, and then there are 4. So the vertical displacement
has regions where it moves the most and regions where it moves the least. And the regions where it doesn't move at all in terms of its amplitude, I'm going to mark by a black dot. These black dots, or these dots, are called nodes. They have no vertical displacement. So any region that doesn't move vertically is called a node. So if you're jumping rope, or if you and your friend are taking the rope and you're shaking it up and down, and suddenly there's a place where it bows up completely, it bows down completely. Technically your hand is moving up and down because that's putting energy into the system. But when you think about it compared to everything else, your friend's hand who isn't moving and your hand, which isn't really moving all that much, we'll just assume it's not moving at all compared to the rest of the rope. Those are also nodes. So this one has 2 nodes, 3 nodes, 4 nodes, and 5 nodes. The arrows mark where the antinodes are. These are regions where vertical displacement is greatest. So points at which it doesn't move are called nodes. Yeah, and you can bring up the sign sheets. Oh, that's homework. Okay. No one look at her. She gets very self-conscious. The places where they move the most are antinodes. So the number of antinodes, 1, 2, 3, 4. The vibration or oscillation is associated with a number, and this is typically labeled as N. For waves in string and air, N is equal to 1, 2, 3, etc. So there, you just use whole energy, or use integers. There is a naming convention for this. And some people have associated N as, when you're thinking about a string, you think about N as the number of antinodes. So if you've got N equals 2, you're dealing with this. It has 2 antinodes and N plus 1 nodes. So N equals 2, antinodes is 2, nodes is 3. And actually, I should say, there are two naming conventions for this. So we're going to learn both of them. There is the harmonics convention. And then there is the overtone convention. Now in 1, 2, 3, 4, etc., for the harmonics convention, it's very easy. First harmonic, second harmonic, third harmonic, fourth harmonic. So the harmonic convention, let me back that up. The harmonic convention is basically the number of n's, the nth harmonic. For every n, its harmonic is nth harmonic. First, 1, first harmonic. 2, second harmonic. 3, third harmonic. Fourth, 4 harmonic. For the overtone, it is fundamental frequency, two is first overtone, 3, second overtone, 4, third overtone, etc. So if you're going to use the overtone naming convention, fundamental frequency, then the first overtone, second overtone, third overtone. The first overtone is the first frequency above the fundamental frequency where you get a recognizable pattern. The next recognizable pattern after that becomes the second overtone, the second time after the patterns began. So these are the naming conventions for these whole things. In a string, the frequencies of this is this, that the nth frequency is n over 2L square root of T over rho. Now really, to simplify this, this is NV over 2L, where V equals T over rho. Now N is the order of frequency, the first harmonic, second harmonic, whatever. The L is the length of vibrating string. V is the velocity of the wave in the string. This velocity is T over rho. T is the tension in the string, and rho is the linear mass density. So this opens up a whole world of multiple choice questions. Let's review some of them now. What is, well, this one's rhetorical. The most common string that you deal with on a regular basis, guitar strings. When you pluck that metal strand, it vibrates. So let's talk about guitar strings for just a moment. You notice that you have thick strings and you have thin strings. The thick strings, when compared to the thin strings, what are different about them? They're, well, not quite. Give someone else this. It's a deeper note, yes. It produces deeper sounds. But physically, how are they different? The mass. The thicker strings have the bigger mass density. Now, as we discussed before, yeah, you can figure out the volume of the string and then compute its physical densities. But in terms of the way that these equations are set up, it's easier just to measure the mass, measure the length, the mass divided by length is its linear mass density. The fat strings have a bigger mass density. So the bigger the string, how does V change? Does V increase or decrease if rho increases? It decreases. So if V decreases, the frequencies do what? They decrease as well. Hence, the fat strings produce lower frequency. Now let's say you're tuning your guitar string and you tighten it. What happens when you pluck it and then tighten the string to the sound? The sound increases, because if you tighten the string, you increase tension. Increase tension, increase velocity. Increase velocity, you increase frequency. So be prepared that for all sorts of variables to be thrown at you, if you increase the linear mass density, how does that change the frequency? What if you quadrupled the tension, how would the frequency change? If you quadruple the frequency, how would the frequency change? It would double. Square root of quadruple is 2. So the frequency would double. So let's do a problem with the string. We'll do the simple one and then we'll make it a touch more complex. So you have a string and it's vibrating in this particular mode. The horizontal is not to scale, but these are the nodes that we have. The frequency that you hear is 3,000 hertz. The length of the string is 2 meters. If the mass of the string is 20 grams, how much tension is in the string? How much tension do you have to put on the string in order for it to vibrate like this? Well, you use F N over 2L, tension over rho. I got to solve for T. F squared, N squared, 4L squared, T over rho. Solve for T. 4L squared, F squared, rho, over n squared is equal to T. Now I didn't give you rho, but it's easily solvable. Rho is mass of the string divided by L. So this becomes 4L squared F squared mass of the string divided by n squared L. And this gives you 4L F squared ms over n squared. So let's put in our values. L, 2. F, 3,000. Mass of the string, 0.02. This has to be converted into kilograms. And then, what's my value of n? What's the value of n? 5. All you have to do is just count the antinodes. 1, 2, 3, 4, and 5. So it's 5. And so it is under the tension of 57,600 newtons. And so that's the tension. Now we're going to do something a little bit more complex, and it could be on the test. When you look at it, you'll go, oh, this is. Say you have a cliff, and you have a pulley right there. You have a mass that's hanging. This is L2. That distance is L1. You have a mass of a string. This is how we fit Atwood's machine into test 3. You have a hanging mass. That mass is providing tension on the string. It produces a frequency and a particular harmonic. So we have the frequency as a function of N, L1, L2, hanging mass, gravity, and the mass of the string. So if you could put together a formula that states the frequency of the vibrating string, given all of these conditions, you should be able to derive any variable within it. So learn how to do this. In this particular case, there is the correct way to pluck the string and a wrong way to pluck the string. This is kind of a common sense question. There's a part of the string that you pluck and a part of the string that you don't pluck because it's not that great of an idea to pluck. Which part of the string do you pluck, L1 or L2? L1. Who in their right mind would pluck L2? The mass would just go wah, 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 just go fling back and forth. It's not held in place. The pulley and the wall are holding that string in place. That's going to be the place where you pluck. For some reason, I always get a noticeable group of students who go, well, you're just going to plug L2 and that mass is just going to make a sound. No, I don't understand why. So, you plug L1, the total length is L1 plus L2. So let's do this. The frequency is NV over 2L, where this L is the vibrating part. So it's L1. The V is the square root of tension over rho. The tension is provided by the hanging mass. So that's mHg. The density of the string is the mass of the string divided by the total length of the string, which is L1 plus L2. So let's start putting this stuff together. This with this becomes that. This and this will go into this now. Rho is in the denominator, so 1 over rho is L1 plus L2 over ms. So this becomes N over 2L1 square root mHg L1 plus L2 all divided by ms. And so that's the derivation. Now I can ask for any of the variables. L1 would be a little bit of an algebraic nightmare to get to. That may be a homework problem or something. But L2, you can solve for any of these things. Let's do, I don't know, we can do L2. First thing that I would want to do, let's say solve for L2. First thing I would do is square it, f squared n squared 4L1 squared mHg L1 plus L2 all over ms. I want to isolate this thing right here. So I'm going to take the denominator, move it up, and I'm going to take n squared mHg and put it down there. So this becomes 4f squared L1 squared ms over n squared mHg is equal to L1 plus L2. Subtract both sides with L1, and I'm left with 4f squared L1 squared ms over n squared mHg minus L1 is equal to L2. And so you should be able to take this and flip any variable out of that equation and leave it by itself, be able to solve for it. Even I could drag it down into this, L1 4f squared L1 ms over n squared mHg minus 1 is equal to L2. So that further simplifies it. Now, one of the things that you could do is you could sit there and go, I don't believe you, Dr. Eschenberg. Prove it. Prove the units make sense. Prove that this garbage right here, I can rely on it. Well, okay, let's do a unit check. Now, length and length means that what's inside this thing has to be unitless. All the units have to cancel because something minus a number must give you another number. So that has to be, this right here has to have no units whatsoever. Well, f squared is inverse second squared. Length gives you meters. Mass is in kilograms N squared, that has no units, that's just a number. mH kilograms, gravity meters per second squared. Kilograms, kilograms, second squared, meters, meters. It is now unitless. So the units do check. One of the things that you, and I never hurts to repeat this, if you're confused and you do a unit check and the unit check works out, you've got a certain level of confidence going on in the problem. So now you can solve for anything. The danger with this is I have to choose numbers that work right. Because you guys always want your numbers. Let's say mass of the string was 20 grams. Let's say that L1 was 0.4 meters. Let's say the frequency was 700 hertz. Let's say that the hanging mass was 800 kilograms. Now, to some of you who say, wait a minute, you're telling me that a 20-gram string is holding up 800 grams of mass? And my response to you is, the string's made out of rebellium, it's really tough, it can take it. That, it's either rebellium or adamantium, one of the two. Now, let's plug and chug. M1, 0.4, 4, F, 700, squared, L1, 0.4, MS, 0.02. In, oh, I need a harmonic. Let's say third harmonic. So N is equal to 3. $800 and 10 minus 1. And who knows what we're gonna get. And to pull back the curtain and tell you what, how I do this, I normally solve for the variable, then I put this in a spreadsheet, and then I just start popping in numbers until I get a series of numbers that work out. This number will not come out pretty. Oh, and it's really not going to come out pretty. Hold on. This central thing comes out less than 1. All right, I need to change. Hold on. All right, the mass of the string is not 20 grams, it is 200. Because if this was 0.02, this thing would be negative and I would have a negative length. And then the whole, and this is what I do on tests. I plug in numbers and I get a negative number first and I go, well, that's not gonna work. So the number I get is 0.47 meters, which means L, the total length, L1 plus L2, is 0.87 meters. It could be that I asked for the total length of the string. Excuse me?
So 0.87 is the final answer?
Yeah, 0.87, the total length of the string. That would be the question that I could ask. I could ask for what harmonic it's oscillating at. I could ask for what is the mass hanging at the end of the string. I could do all sorts of fun things with this. All right, moving on. So that's a simple example of, or a couple of examples, dealing with the vibrations of string. Now we deal with pipes. Now, in the idea of pipes, there are two major types of pipes that we deal with. One is, you can think of a flute. Flute open at both ends is a type of pipe. A pipe open at both ends. Then there is what I call a half pipe. It is a pipe closed at one end. When you do your speed of sound and air lab the week before Dead Week, you're using effectively a half pipe, because in the lab you have a big tube and you control the level of water in that tube, and the length of the tube is the part of the tube not submerged in water. The water acts like the sealed end of a pipe. So pipe and half pipe. The equation that you use for the frequencies of a pipe that this thing will resonate is NV over 2L. L is obviously the length of the pipe. N is the harmonic or overtone or fundamental frequency, whatever you want. And then V is the speed of sound in air. If you have the book or you look it up on Wikipedia, the velocity of sound in air varies as a function of temperature. The hotter it gets, the faster sound moves through air. The whole purpose of the velocity of sound in air lab is to numerically acquire that value. It is going to be approximately about 345 meters per second. In Physics 213, I round it because I'm not interested in having you guys try to play with the velocity of sound in air. And it's among the same reasons why I use gravity as 10. It just makes things mathematically easier to solve for. I say the velocity of sound in this room, on problem sets, on the test, is 350 meters per second. Done. It's a nice round number. It's clean. It helps me speed things along. Trying to get the numbers to work with 343.28 whatever just makes it a nightmare. 350, I can get the numbers to work pretty nice. For a half pipe, the frequencies are NV over 4L. L is the length from end to end of that pipe. V is the velocity of sound in air, N is the order. Now, in the rope, the amplitude was the displacement vertically. The amplitude in sound is the overpressure or underpressure of the air. What is sound? How is it formed? The vocal cords in my throat vibrate as the air passes over it. This causes regions of compression and decompression to come out of me and head towards you and fill the room. So as I'm speaking, if we could slow down time really slow, and you could see pressure of the air, that there would be regions like walls heading towards you where the pressure is slightly above standard pressure, and there are walls heading at you that the pressure is slightly below. So this would be like 1 atmosphere, and then the oscillations occur slightly above and slightly below. It's not that big of a pressure difference. We could talk about decibels and sound pressure and stuff like that, but maybe next week. And what that does is the constant overpressure and underpressure enters your ear canals, and that overpressure or underpressure causes your eardrums to vibrate, which then pushes on the 3 little bones in your ears. I'm a physicist. I don't know all these body parts. I'm sure you could go to a biology class and learn it in there. But the bones start to vibrate or oscillate, and they push up against the fibers, and then it turns into a neurological mess, and then your brain hears it. That's what sound is. It is your brain's perception of the overpressure and underpressure that my voice box is producing. Now, as I told you before, when I initially presented it, in goes 1, 2, 3, 4, 5, etc. There is an exception to that rule. There always are exceptions. Where is the exception? Half pipes only have odd ends. For a full pipe, N equals 1, 2, 3, ... The half pipe, N equals 1, 3, 5, ... 2, 4, 6 do not exist. Now there's a derivation for this. We won't go into it. Just 5-second explanation. You can treat a half pipe the same as approximately equal to an open pipe of twice the distance. So a half pipe closed in has the same harmonics as a pipe that's twice as long that's opened at both. And we'll leave it like that. This means that for strings, which my symbol is this, and full pipes, we have first harmonic, second harmonic, you get the picture, third harmonic, fundamental frequency, first overtone, second overtone, etc. So the string harmonics and the full pipe harmonic naming conventions are the same. For a half pipe, the evens don't exist. There are multiple choice questions that say, given a pipe closed at one end, what is the frequency of the fourth harmonic? Answer, there is no fourth harmonic. Even harmonics do not exist for a pipe closed at one end. So harmonics go first harmonic, third harmonic, fifth harmonic, seventh harmonic, etc. But the overtones, they're the same in some respect. They go fundamental frequency, then first overtone, second overtone, third overtone. The way that the overtones are decided is all by the whatever is the next recognizable pattern, that becomes the next overtone. So for overtones, it always goes fundamental frequency, first overtone, second overtone, third overtone. The fact that the first overtone is associated with the third harmonic in a pipe closed in one end, overtones don't care. Just like honey valve. So for a pipe opened at both ends, first, second, third, fourth, fifth harmonic. For a pipe closed at one end, first, third, fifth, seventh, ninth. For the overtones, it doesn't change. The naming convention remains the same. Fundamental frequency, first overtone, second overtone, third. And that's the naming convention of all of this. So if we have as an example, so you have a pipe, the fundamental frequency is 600 hertz. So fundamental frequency, N equals 1. What is the length of the pipe? You would go, great, F equals NV over 2L. L is NV over 2F. N is 1, V is 350. Now in lab, you cannot assume that the velocity of air is 350. You gotta assume that it is in the 340-ish range. The frequency 600, that means that the pipe is 350 divided by 1200, or 0.29 meters. And there we go. So that's a simple example. Now what I'm gonna do for the last bit of the lecture, and yeah, we're leaving early, is briefly discuss the speed of sound in Air Lab. What's gonna happen is you're gonna divide up into bigger groups. You're not gonna have 12 of these things running around. Probably 6 tops. A lot of times we only do 4. You have a tube, and this tube is attached to a jar with a little lid on the top. And if you lift this jug up, the water flows into the pipe. If you lower the jug, or the water drains out of the pipe into the jug. And remember when you do this, unscrew the top of the jug just a little bit because you need air to go into the jug to replace the water that comes in or goes out. You're going to be given tuning forks. Now, when you do this tuning fork, they're going to give you a little mallet, and you're going to strike the mallet onto the tuning fork, and it's going to go bang. What you do is on this tuning fork, when you initially bang that tuning fork, you're going to get a lot of different frequencies, and you can hear it. But you only want the one frequency which the fork was designed. In order to do that, you pinch the tuning fork at the base, right where it meets the handle. You just go, touch, let go. Don't hold down on it, then it'll kill the sound. You just tap it on either side at the same time. So you get a frequency out of this thing, and while it's still ringing, you hold the tuning fork above the opening of the tube. And then you lower or raise the level of the water. And when you hit that resonating frequency, let's say you had the tuning fork and it's the tube. This is the resonating frequency level at which it's going to resonate. If the water level is up here, you just hear the normal tuning fork sound. If it's down here, you get the same thing. But if the water level drops or rises to a point where it gets to that resonating frequency, where it enters a harmonic, if I'm dropping the water level, it just goes, and when you sit there and you all laugh at me, and I get it, but when you hold that tuning fork, hold it right over the opening, and that thing resonates, you're gonna go, that's it. That's what he was talking about, because it goes very soft and then it just goes bam, and then it backs off and then as it falls. So what you're looking for are the levels at which that happens. This thing is like 1 to 1.2 meters long. There are probably at least 2, if not 3 places where this thing's gonna resonate. I'm going to help you before you even start this thing, let you know where to look, give you the equation, give you the tools with which to do this. Because you're facing the practical reality of that tuning fork is not going to resonate forever. So you got to get in and get your business done. There's no point looking for the resonation in an area where it's physically impossible. NV over 4L will give you the frequency. Rearranging this, L is equal to NV over 4F. N equals 1 means that length 1 is V over 4F. N equals 3, L3, 3V over 4F. And N equals 5, L5, 5V over 4F. What my instructions do is give you a ballpark range to look. You will use velocity of about 350. If you want, you could use 345. 350, 345, it's going to give you about the same answer. Let's say I gave you a tuning fork of 400 hertz. Now, what you should do when you enter the room is look down at your table and identify what tuning forks the TA has given you. Those tuning forks are your Fs. So what you do is you take that first tuning fork, 400, and you plug it into this, 350, 4 times 400, 3 times 350, 4 times 400, 3 times 350, or I'm sorry, 5 times 350, 4 times 400. And you calculate this. So the first one is at 0.22 meters. The second one is at 0.66 meters. The next one is at 1.10 meters. Now the tube typically is only 1 meter long. So what you would do is you would say, well, n equals 5 doesn't really mean much because I can't find it. But I know n equaling 1 and 3 will work. So what you do before you start banging away on that tuning fork is you lower the water to about 20 centimeters down, just above the range. And then when your friends bang that tuning fork and hold it over, you start dropping and you immediately start listening to that resonation. So it's going to go 20, 21, boom, 22, 23, 24, and you go, all right, it resonated at 22. It's almost like you could do the lab before you even walk in. It may not be exactly at 22 centimeters, but it's going to be darn close. And then there's no point to look at 25, 26, 27, 28, 29. You're wasting time. Stop the tuning fork, lower it down to 64 centimeters, bang it again, and then repeat the process and search for that area. And I promise you, if you hit that frequency and hit that resonance, it is noticeable. Sometimes if the tuning fork, if you've got enough energy on that tuning fork, the water will vibrate a little bit. It'll create, you'll see little droplets form. That's because the energy is resonating and banging off that water so hard, the water gets popped up into the air. These are some of the examples that we use with sound. Next week we will still cover sound, and next week will be the last week of new material. Be sure you put your name on the sheet of paper at the front. I need the third sheet so that everybody gets credit.